Now we're off to the next chapter, 9, Fractional Equations. So we've been continually building on our relationships that allow us to handle equations, fractional equations, whole numbers, literals. We've got quite a toolbox that we're assembling here to help us to do math related to electronics. So in this section, we're going to look at, or in this chapter, the general equations, real equations, applications, and then just as I promised from the last section, the quadratics, solving and factoring using the quadratic equations. And we found that the statement was in the previous chapter that there are situations when it requires the use of resorting to the quadratic equation to solve for unknowns. So we're going to be solving, and using the quadratic to solve second-degree equations. An algebraic equation is a mathematical statement then containing one or more variables separated by equals signs. Okay, so in the example here, 5x equals 3y plus 7. We can take that relationship where we have two literals, two variables, and set it up to solve for either one of those. This one quite easily, because each term is pretty independent. We can move it around to the right or left side to get it to where we need to solve for x or y. Later we're going to find out how we solve one in terms of the other. Rule 9 then says to solve an equation that includes fractions or mixed numbers. Again, we get rid of the fraction or the mixed number. We solve for the unknown, and then the last step is always to verify. We may not always do that. I will leave that up to you. So in a relationship here, this expression 1/3 plus a over 4 equals 2. We're going to start moving the terms around so that we get that a on the left side by itself, so that we have all of the real numbers or the whole numbers there to solve for. So the first thing we're going to do is we're going to subtract 1/3 from either side. This leaves us with a over 4 equals 2 minus 1/3. I hope that as you're doing these, you're starting to get a feel for setting up a strategy, how you can move things quickly without having to do add this, subtract that. You just start looking at it and knowing that, well, if I move it to the other side, I change the sign and subtract. So now we have a over 4 is equal to, well, we can't combine the terms on the right side because we don't have a common denominator. But we do know that 6/3 is equal to 2. So if we take 6/3 minus 1/3, we get 5/3. Now the last step is we're going to move that 4 to the right side of the equation, in essence by multiplying both sides by 4. So we get a equals 4 times 5/3, which gives us 4 times 5, or 20, divided by 3. And by moving things around and in essence reducing, we get 6 2/3, an improper fraction to a mixed number. In this one, solving by x requires just a little more work. Again, we look at the strategy. How do I get that x in the denominator for x minus 1 into the numerator and get all of my real numbers on the right side of the equation? So the first thing we're going to do is we're going to move all of the real numbers that we can to the other side. So in this case, we're going to take that 1/2 and move it to the other side. So since it's a minus 1/2, it becomes plus 1/2 when we add it to both sides. And then we're going to change 2 to 4 halves plus 1/2, which gives us 5 halves. Okay, now we have a term that says 5 over x minus 1 is equal to 5 halves. So we need to do a little more manipulating. So what we're going to do then is we're going to move the 2 out of the denominator to the other side by multiplying both sides, and then we're going to multiply both sides by x minus 1. So although it looks like I've skipped a step here, that's in essence all we're doing, is we're normalizing this relationship. So I have 2 and x minus 1 on one side, and 2 and x minus 1 on the other side. Well, we can see on this side, the x minus 1s quickly cancel out, and I'm left with 2 times 5, which is 10. And then on the other side, my 2 cancels out, so I'm left with 5x minus 5 when I combined these terms and take the product. So let's again leave the 5x on one side, and all of the real numbers or whole numbers move to the other side. So I get 5x. In this case, I'm adding plus 5 to both sides to give me 15. And then the last step being divide through by 5 on both sides. X is equal to 15/5 or 3. The best way to learn how to do this is I've shown you this example. Now go back through and try it yourself. Set up the problem and do it step by step, and try it yourself and prove it to yourself that it in fact works. Okay, let's take a look at an example here. Okay, in this case, we've taken the 3, and I did do a solution for you. Okay, so we're substituting to verify in this example that it did work. Like I said, I don't always do that. I leave that up to you to test to make sure that it does work. These are examples out of the book, so I'm hoping the author was correct. Okay, another problem here. General equation, solving for x. We have x in 2 terms, x plus 2 and x minus 3, okay, on one side, and then x plus 2 on the other side. Well, this one is nice because it's set up for us that we have a common denominator. So let's just take the 2 terms with the common denominator, x plus 2, and combine them on the right side of the equation. So in doing so, I have 4 over x plus 2 minus 2 over x plus 2. They combine nicely. I end up with 2 over x plus 2. And now I'm down to just 2 terms here that do, in fact, have uncommon, or they do not have a common denominator. So again, I can simply flip these over. As long as I do it from one side and do it to the other side, I can easily flip these over so I can get those x's in the numerator, x minus 3 and x plus 2. What I'm going to do is I know by inspection that 3 plus 2, that the lowest common denominator has to be 6. I can't go any smaller or any different than that. So I'm going to multiply 6 by both sides, and that will, in essence, give me a value of 6x minus 3 and 6x plus 2 on this side, okay, which I can then reduce. 3 into 6 gives me 2, 2 into 6 gives me 3, and I can reduce those terms, okay. Now, in the reduction, 2x minus 6 equals 3x plus 6. I can move my terms around here, solving for x. Let's move all the x's to the left, all the real numbers to the right, and I end up then with 5, or 1x, not a negative x. A negative x is equal to 12, okay? I can move minus 1 to both sides, and that's how I end up with x equals minus 12. Okay? Perform a check by substituting the minus 12 back into the relationship for x. Now we look at some examples from electronics. We've got a relationship here where we've got voltage and resistance. We want to solve for the voltage or the resistance in this case, given terms for voltage, okay? So in this case, I don't have any values given, but what we want to do is look at how do we just move terms around. It's usually a lot easier if we set up our solutions by solving for, with the unknowns, the values. Okay, so if we're given voltage 1 is equal to the quotient E times R1 and the R1 plus R2 in the denominator. Now I start moving my terms around. I'm going to take the R1 plus R2 out of the denominator by multiplying it by both sides. So this simplifies that. These two terms cancel out. I'm left with R1 plus R2 on the left side. Okay, now I've got V1R1 and V1R2 in the next step here is equal to E times R1. Okay, what I'm doing here is I'm gathering terms. I'm trying to gather terms together so that I can solve for, in this case, R1. Okay, that's exactly what they want us to solve for. Hint, that's what was given to us in the problem. Okay, so now what I'm going to do is I want to look at all the terms that have R1 in them. I'm going to gather them to one side. Anything that doesn't have an R1 goes to the other side. Okay, so I have V1R1, that's a keeper. V1R2, that's going to the other side. Minus E R1, that's a keeper, equals 0. Okay, so now if I subtract this term from both sides, I will end up with V1R1 on one side or V1R2 on one side and V1R1 and the R1 values on the other. So I'm gathering my terms. I can then factor out my R1s from both of these terms, and I'm left with R1 isolated, which is good. That's the goal we're looking for, is times the value in parentheses V1 minus E. I can take that then and divide through on both sides. Again, I'm not showing that here, but that's what you can do. Write it down on your own paper and work through it. And so now I have R1 isolated as minus V1 R2 V1 over E. Okay, so I'm taking a look back here. V1 R1 E. I moved that here. That here. Okay, so I think I've got a sign problem here because this does not match here, and I suspect where it is, I want you to check this, is this value here. When I moved it to the other side, that should have been a negative right there. Okay, so alternatively, they're showing us, okay, let's take it right from this step right here and factor. So we're going to factor out our values for R1 and R2. Okay, again, we're moving them around left and right. We are gathering our terms so that in essence we have R1s on the left side and R2 on the right side. Gathering, factoring, we end up with R1 equals V1 over R2 E minus V1. Okay, in this application, we're going to look at current and conductance. We've got an equation here where we are, in fact, given values. We're given a current value of 2.73 milliamps, a total current value of 6.75 milliamps, and a conductance of 370 microsiemens. Remember that the inverse of ohms is Siemens. So we want to find the conductance in G2. So we take the expression that was given to us and we're going to move the denominator out and multiply by both sides. So in doing so, I have the current times G1 plus G2 is equal to the total current times G1. Okay, now the next thing I'm going to do is multiply both sides by I1 so that this current I1 and this current I1 cancel, and I'm left with the current total, the conductance 1, and I1 on the right side of the equation. Once I do that, then I have these terms freed up. I can start moving them around. Okay, since I'm solving for G2, I'm going to move G1 to the other side of the expression. Okay, so now I have G2 all by itself. I have the total current, the total conductance, and the current I1 minus the conductance G1, all on the right side. Now start plugging in your values for IT, G1, I1, and G1, okay, in each of these places where they are currently literals, and solve for conductance G2. Again, the trick is going back and taking that number, taking all the numbers, sticking them back in the original expression, and make sure that your answer, in fact, is correct. Okay, now we're finally to that scary thing called the quadratic equation. The quadratic equation gives us a way to solve for relationships that appear to be unfactorable. Okay, everything we've seen in the past, we've been able to take guesses and or come up with some solutions by trial and error to solve for what are called the roots or the solutions to the problem. Okay, to do this, we have to look at the quadratic form that the equation is in, the standard form. That standard form is some coefficient a times x squared plus some coefficient b times x plus c. Okay, these are the means, these are the extremes, and set that equal to 0. Okay, it has to be in that form to do the next step. The next step is we use this standard form, the quadratic equation, minus b plus or minus the square root of b squared minus 4 times ac divided by 2a. So what we have here is a handy-dandy relationship that allows us to solve for the roots if we have an unfactorable relationship. The nice thing about this is you can take this quadratic equation and program it into your calculator. Some of your calculators have it built in. You can program it into Excel and have it solve for you. So you don't have to go through the grinding every time of entering these numbers. You create some fields and arrays, B, A, and C, and then write this relationship into Excel, and you will have a handy-dandy way of solving for the quadratic equation every time. When solving for the unknown in a second-degree equation, there will always be two possible solutions called the roots. Sometimes we can factor the quadratic then to the two roots, and we use that relationship. If the quadratic's not factorable, then, as I said, you have to use the quadratic equation. Quadratic equations that have no x term are called pure quadratics. Okay? Such equations are readily solved by moving the constant to the right and finding the square root of both sides. We've seen this before. We saw this in section 8. So what looks like a quadratic here with no mean term in the center here, x squared minus 25, I can simply add 25 to both sides, and I get x squared equals 25. Again, take the square root of the square. I get the square root of 25. That x does not belong there. Let's get rid of it. I don't know why it's there, or if it will even let me. Yeah, it did. Okay, good. So, don't know how that got there. Gremlins. So then, when I take the square root of both sides, now I end up with, look at here, I got a plus and a minus. Okay, because I can get a plus and minus. If I take minus 5 and minus 5, I get 25. Solving by factoring. So now we're back to solving by factoring, not using the quadratic equation. So a trinomial then is of this form. Notice there are no leading coefficients other than here. There's no a on the beginning here. We just have b. So this can be factored if we can find two numbers whose sum is the coefficient of the second term and whose product is the third term. They used the extremes and means in the previous chapter. So we have this form where a is understood to be 1, 7 is b, and 12 is c. But in this relationship, I can start then taking some guesses to look at what sums to make 7 and what multiplies to make 12. Well, this one, the author made it pretty easy on you. 3 and 4 are our only choice. 3 and 4 sums to make 7. 3 and 4 multiplies to make 12. So now we are easily solve for our roots. Our roots in this case are minus 3 and minus 4 by setting each term to 0 and solving for the unknown. Okay, that's a simple way to do it. It's not always that easy. Typically in exercises like this, the author gives you a way to quickly look at and learn how to do this pretty much by inspection. Okay, so if we take a look at this one, x squared minus 3 minus 6 equals 4. So now I don't have a 0 here. So what do? Well, I got to create a 0. I got to multiply, or I got to subtract 6 from both sides of the equation, or 4. Subtract 4 from both sides of the equation so that I get 0, so that I have the standard form here, so I can do my means and my extremes guessing. So subtract 4 from both sides. Now I get x squared minus 3x minus 10 equals 0. Now I need two numbers that when summed together gives me negative 3, and when multiplied together gives me minus 10. So very simply, if I add 2 to minus 5, I get minus 3. If I multiply 2 and 5 together, where I have a negative, I get minus 10. Okay, so it factored out to x plus 2, x minus 5. Set each of these terms to 0 and solve for the unknown. So our roots in this case are x is equal to minus 2 and x is equal to 5. Okay. All right, so now we've seen how we can solve with and without the quadratic equation, the form it has to be in order to solve. So if we have, again, an example here, relationship 2x squared, where a is 2, 4x, b is 4, minus 14, that's our value for c. So now in this case, they're saying, well, why don't we go ahead and factor it and use the standard form. So you can factor that 2 out, just makes things a little easier later. You can factor that 2 out, and now I have x squared plus 2x plus 7. Okay, I can use the quadratic equation, put my terms in here for b, a, and c, and solve, and what I end up with then now are my two roots, minus 3.8 plus 1.8 as our roots. I would suggest that you try to have some fun with this. Either look on your calculator and see if your calculator has the form on it to do a quadratic. I'm going to check this one out, the one I recommended to you, and see if it has the quadratic equation built in. And then also play with with Excel. Excel is kind of interesting to program. And so that gets us through Chapter 9 of Algebraic Fundamentals.